Okay, this is section 9.1. This is the beginning of the chapter on differential equations. 9.1 is more of an introduction and how to verify and kind of what the idea of a differential equation is. Um, in its very basic sense, differential equations are simply equations with derivatives in them. Get a different color there. There we go. Derivatives. And we've already dealt with differential equations in the past. Something as simple as like, I'll just put this off to the side, dy over dx equals x squared. Okay, that's a differential equation. Um, we've had to find the antiderivative of that. The antiderivative of dy over dx is simply y. The antiderivative of x squared is 1/3 x cubed plus some constant c. So the original equation was a differential equation. Differential equations, however, do not have to be limited to things which are that basic. They can have second derivatives in them. They can have combinations of derivatives, first derivatives, third derivatives, second derivatives, whatever. There's all kinds of differential equations. We're going to go through some of the basic ones in what we're doing. And not that we're going to get into anything this high order, but there's an entire class dedicated to differential equations because they can go into much higher order stuff and applications and things like that. What we are going to do is get the idea of what these things look like. So if we're going to call y equals f of x the particular solution to a differential equation, we're simply going to verify that some of these solutions actually work. So our differential equation is y double prime minus y equals 0. So as you can see, y double prime is a second derivative, therefore it has a derivative in the equation. We want to determine if the following A, B, and C are actually solutions to that differential equation. In other words, if I take that function and plug it in for these to the differential equation, does it satisfy the equation? So since the equation is y double prime minus y equals 0, we are going to need a second derivative. We need to be able to plug the second derivative in there. So given that y equals sine of x in letter A here, we need the first derivative, which of course is cosine of x, and we need the second derivative, y double prime, which is the negative of sine of x. So we're going to go ahead and substitute negative sine of x into y double prime in the equation. So that would be negative sine of x minus the original y value, because that's what this piece is sine of x equals 0. Negative sine of x minus sine of x is not 0. It is negative 2 sine of x. So we'd be saying that negative 2 sine of x equals 0. And that is not a true statement. Okay, that's a false statement. So this, letter A, is false. Does not satisfy. All right, let's check out letter B. Y equals 4e to the negative x. Once again, we need y double prime. To get there, we need y prime first. The derivative of 4e to the negative x, using a little bit of chain rule here in exponentials, is negative 4e to the negative x. Y double prime, again, using that chain rule, bringing out the extra negative, gets us back to 4e to the negative x. So now we're going to plug this stuff in. So I've got y double prime, that's 4e to the negative x, minus the original y value, which is also 4e to the negative x equals 0. And then, of course, the left side subtracts to 0. So this one is true, meaning that 4e to the negative x is a solution to that differential equation. There can be multiple solutions to differential equations, especially ones that have higher order derivatives in them. So there can be a whole bunch of different things. Let's check C. Let's see if C works. So once again, we need y prime. C here is a constant, so it's constant e to the x. The derivative, of course, is just the constant e to the x. Y double prime, same exact thing. It's the constant e to the x. So let's plug that in. We're going to get y double prime, which is c e to the x, minus the original y, which is c e to the x equals 0. The left side becomes 0. So this is also a true statement. So B and C are both solutions to that differential equation. Okay, that's just verifying whether certain given functions are solutions or not. All right, let's take a look at the second page. This one says, for x, y prime minus 3y equals 0, verify that y equals cx cubed is a solution. When it says to verify something as a solution, they're telling you it does work. You just need to show it. So we'll do that. And then we want to find the particular solution if y equals 2 when x equals 3. The particular solution means we're going to be able to figure out what that c value is given the fact that y is 2 and x equals 3. And that's basically going to, I don't know how much you remember about this, but when you take antiderivatives, you are getting a family of functions, and this is going to eliminate the family and give us the one particular solution when it crosses through the point 3, 2. All right, so let's first verify, because that's what it says. So to verify, let's see, I've got x, y prime minus 3y. I need a y prime and I need y. They gave us y, so let's find y prime. So y prime, this is going to be cx cubed. C is some constant, so this is a power rule. It's a polynomial, so we'll use a power rule. So it's going to be 3c x squared. Let's see a little bit bigger there. 3cx squared. So let's go ahead and plug this stuff in. Let's see, it's got x times y prime, which is 3c x squared, minus 3 times the original y, which is c x cubed, equals 0. Okay, verifying should mean, again, this means this should work, so we just have to show that it does. Well, distribute the x into the first parentheses, and you're going to get 3c x cubed. Distribute the 3 into the second parentheses, you also get 3c x cubed. Subtracting those does indeed give you 0. Therefore, the verification works. The second part says we want to actually find the particular solution if y equals 2 and x equals 3. Well, in order to do that, given the fact that we actually know that this is a solution now, we just have to simply plug in y equals 2 and x equals 3 into our y equals cx cubed. And we'll get our particular solution. So if we plug in 2 for y, c is what we're looking for. We'll plug in 3 for x, so that's 3 cubed. So 3 cubed is 27, so we're going to get 2 equals 27c. Dividing by 27 gives us that c is 2 over 27. So our particular solution is y equals 2 over 27 x cubed. Okay, obviously, like I said, not all of them are going to be that short and easy, but this is the general overall concept of what we're doing. This is just a very basic introduction. Keeping this under 9 minutes is a good thing. So that should be all you need. Good luck.